You're staring down at a digital Earth, not a globe, not a model, an entire planet rendered as pure, living information. Data pulses through continents like neon arteries. Data centers glow like stars. Billions of users are tapping, clicking, buying, searching, and messaging in real time. Every second, the world produces more state changes than the human eye can track. Every tiny action, every swipe, every login, every ad impression creates a moment in time that must be stored somewhere. Now imagine you're responsible for making sure all of those moments stay true. Imagine guaranteeing that whenever a piece of data changes in Tokyo, the systems in New York and London and Singapore all agree on exactly when it happened. Imagine building a database that doesn't just store the world's information, it keeps the world's information synchronized across oceans, across time zones, across the physical limits of physics itself. That system exists, and it's called Spanner. Today, we're diving deep into one of the most extraordinary engineering achievements ever built, Google Spanner, the world's first globally distributed, externally consistent, synchronously replicated, multi-version database. This system didn't just push boundaries, it ignored them entirely. Before we start unraveling how Spanner bends time, conquers distance, and keeps the entire planet in sync, make sure to like this video and subscribe to the channel. It seriously helps grow the community, and it tells YouTube that you want more deep dives into the technology that runs the modern world. Alright, buckle up. Let's explore the database that treats the globe like a single machine. Let's explore Spanner. To understand Spanner, you first need to understand the impossible problem it set out to solve. Google's infrastructure grew to the point where a single data center was no longer enough. Not for search, not for Gmail, not for ads, not for YouTube. Everything had to be replicated. But replication comes with a brutal trade-off. The more copies you have, the harder it is to keep them consistent. Bigtable, one of Google's most famous systems, powered incredible applications. But it lacked transactions. It lacked schemas. It lacked strong consistency across data centers. And in a world where applications needed correctness, atomic changes, and guaranteed ordering, Bigtable wasn't enough. Engineers tried Megastore next, a system that delivered synchronous replication and a semi-relational model. But it was slow. It was constrained. The write throughput just didn't scale. Google found itself stuck between two worlds. The NoSQL world, where scale was easy but consistency was painful. And the relational world, where consistency was strong but global scale was, well, basically impossible. So Google did something wild. They set out to build both at the same time. A database that could scale like a NoSQL system. A database that could transcribe the truth of the world like a relational system. A database that wouldn't just store data, but store time. So how do you build a database for the entire planet? You start by creating a universe. Yes, that's the actual name. In Spanner, a deployment is called a universe. And inside that universe are zones, clusters of machines located in various data centers. Each zone contains hundreds, sometimes thousands of span servers. These span servers don't just store data, they replicate it, coordinate it, and communicate with other zones to keep everything consistent. If you turn to the organizational diagram early in the Spanner paper, you'll see the architecture laid out like a constellation. A universe master watches over everything. A placement driver orchestrates where data should live. Each zone has a zone master assigning data to workers. And then you have the span servers themselves, machines holding between 100 and 1,000 tiny partitions called tablets. Think of tablets as little containers of key-value versions. They hold data, history, timestamps, every version of every row, stored in a B-tree-like structure and written to Google's distributed file system, Colossus. Every tablet is part of a Paxos group, replicated across multiple servers. Paxos is the engine that drives consensus, ensuring that writes happen in the same order on every replica, no matter where they are. A database built on Paxos is already impressive, but it's nowhere near enough to do what Spanner does next. See, Paxos solves agreement, but not time. And time is the hardest part of global consensus. Imagine you ask a data center in Europe to agree on the order of two writes, one made in California and one made in Singapore. The speed of light itself becomes your enemy. Messages take milliseconds, networks jitter, clocks drift, machines disagree. You can't simply say, this happened first or that happened second, unless you have a universal clock. But universal clocks don't exist. At least, not until Google built one. Enter TrueTime, the beating heart of Spanner. TrueTime is not just a clock API, it's a philosophical reset. Instead of pretending clocks are perfect, TrueTime acknowledges the truth. Clocks are always uncertain. They drift, they skew, they lie. So TrueTime exposes that uncertainty directly. Call TT not now, and you don't get a single number, you get an interval. An earliest possible time, a latest possible time. The real time is somewhere in between, and as long as you stay within the safety bounds of that interval, you know your timestamps are safe. How does Google keep uncertainty low? That's where things get almost science fiction. TrueTime relies on two independent time sources, GPS receivers, listening to satellites in orbit, and atomic clocks, oscillators so stable they drift only microscopically. Each data center has a fleet of time masters, GPS-backed machines, and Armageddon masters equipped with atomic clocks. Every machine pulls multiple masters, filters out liars and outliers, and keeps its internal notion of time accurate to within a handful of milliseconds. If you look at the TrueTime graphs in the later pages of the paper, you'll see that most machines sit around an uncertainty of just a few milliseconds. That tiny window, just a few thousandths of a second, is what allows Spanner to do the impossible. Because now, Spanner has timestamps it can trust, timestamps it can use to order transactions across the globe, timestamps that satisfy something called external consistency, meaning that if one transaction finishes before another one starts anywhere in the world, their timestamps reflect that ordering. And this one guarantee unlocks everything. Let's walk through what actually happens during a transaction. When a transaction writes data across multiple Paxos groups, each group's leader participates in a classic two-phase commit. But Spanner adds something special. The commit timestamp is chosen not randomly, not locally, but using TrueTime. The coordinator leader chooses a timestamp that is greater than any timestamp used before, greater than the latest possible time returned by TrueTime, and guaranteed to be safely in the past after waiting out the uncertainty interval. This waiting period is called commit wait, and it's brilliant. Spanner literally pauses for just long enough to be certain the chosen timestamp is already behind the real time of every machine in the system. Once commit wait finishes, the transaction's timestamp is universally valid. Every replica can apply the write. Every read can reference it. Every other transaction can be ordered after it. Spanner doesn't just store data, it stores history. A timeline of the world, precise down to the millisecond, shared by every data center on Earth. And it gets better. Because of its timestamping system, Spanner can serve snapshot reads, reads that ask the database, what did the world look like at time t? This lets you run consistent backups. It lets you run MapReduce jobs across a frozen moment in time. It lets applications read without blocking ongoing writes. It even enables atomic schema changes where thousands or millions of tables update seamlessly across data centers. Spanner's read-only transactions are lock-free. They can execute on any replica that's sufficiently up-to-date, which means massive throughput and low latency. In the micro-benchmark section of the paper, single replica snapshots, multi-replica snapshots, they all scale beautifully. The throughput skyrockets as replicas increase. Meanwhile, commit latency stays consistently low thanks to parallel Paxos operations. When failures occur, like when the paper describes intentionally killing an entire data center, Spanner recovers automatically. Leader leases expire. New leaders are elected. The system converges back to full throughput within seconds. This is what happens when you fuse consensus, replication, and time into a single design. Now let's talk about a real-world application of Spanner. F1, the database behind Google Ads. Before Spanner, F1 ran on a manually sharded MySQL deployment. Tens of terabytes of data. Hard-coded customer-to-shard mapping. Complex cross-shard logic. And resharding? a multi-year nightmare involving dozens of teams and massive operational risk. Spanner made all of that disappear. F1 moved its entire backend onto Spanner, gaining automatic resharding, synchronous replication across the US, transactions across arbitrary data, consistent global reads, secondary indexes built using Spanner's transactional APIs. Suddenly, a database powering one of Google's biggest revenue engines could scale automatically, fail over instantly, and maintain correctness across oceans. According to the diagrams and tables in the paper, most F1 customer directories fit within a single fragment, meaning Spanner can serve almost all customer operations locally on a single server, even though the system itself spans continents. It's hard to overstate how transformative that is. What used to require handcrafted data engineering, manual operational playbooks, and constant risk now happens automatically. That's the Spanner effect. Let's zoom out one last time. What did Google really build here? Spanner isn't just a database, it's a new kind of infrastructure, one where the world is your data center, time is part of your API, consistency is no longer optional or expensive, scale doesn't require compromise. Spanner bridges the worlds of traditional databases and globally distributed systems. It gives developers transactions, schemas, SQL-like querying, alongside replication, sharding, fault tolerance, and world-spanning distribution. It took Google more than 5 years to get Spanner right, but the result is extraordinary. A system that redefines what's possible when you stop thinking in terms of machines and start thinking in terms of planetary infrastructure. Spanner is the database that treats Earth like a single logical computer. And it all works because of one audacious idea. You can distribute trust if you bound time. If you enjoyed this deep dive into Spanner, the time-bending, globe-spanning database that keeps Google running, please like this video, subscribe to the channel, and drop a comment telling us which groundbreaking system you'd like us to explore next. Your engagement helps this content reach more people, and it lets me keep making these long-form explorations into the technologies shaping the world. Thanks for watching, and I'll see you in the next one.